and marine environments.
From the glaciers carving out streams and river valleys to continuous natural events that shape our landscape, we are fortunate to have the natural treasure that is the Champlain Valley watershed. However, we don't always value the functions of our natural systems. Indeed, human activity over time has dramatically impacted our environment, including our water systems.
It was really the European settlers who forever changed the lake when they arrived, and the biggest change came in the 1800s when they cleared the land for agriculture.
At some point in the middle 1800s, at least some of the counties in Vermont were 80% or more cleared land. Very much the opposite of what we are today. So today we're the Green Mountain State. In the past we might well have been the Brown Mountain State.
When you don't have trees, then you've changed the dynamics of the system. Water that would be evaporated or transpired by trees is now going into the soil. The roots of the trees that held the soil in place are not there anymore. So you tend to have more runoff, that is water moving across the top of the soil rather than moving down into it, and a change in the general dynamics.
And so many of our issues with sediment, sediment now being termed as a pollutant in many ways, in many places, and the phosphorus attached to that sediment are in fact probably the result of this clearance and the legacy sediments surrounding our streams.
Then we started mining gravel for roads, and then we started intensive agriculture with fertilizer and larger dairy herds, and those had impacts on the waters. And then we started building lots and lots of paved roads and shopping lots and suburban housing developments, and all of those as well changed how the water flowed into the rivers and streams.
In the early 1990s and extending into this century, extensive suburban development, so-called urban sprawl, occurring in this area.
And unfortunately, when we pave over the landscape, we create more impervious areas. Every time you put a roof on a building, or every time you put up a parking lot, or put up a sidewalk, there's that much land available for the water to infiltrate into the ground. And that's quite often how most of our water is being purified, by the microorganisms that are taking, eating the stuff that we really don't want, that show up in our drinking water supplies.
We now know well enough how to manage stormwater from new developments. So we can design new developments so that we can minimize the runoff of stormwater. So we're seeing an increased number of developers and engineers and builders who are interested in green design. They want to build correctly, and there's a market for building correctly. There are a number of alternatives that range from very simple technologies like simple rain barrels that are put on individual gutters to capture runoff from individual rooftops, to small rain gardens that will capture the runoff from an individual homeowner's lot, to porous pavement options that allow us to infiltrate rainwater back into the soil rather than have it run down the street the way that it would have before. We now know that the amount of phosphorus, acre for acre, that's being delivered from urban areas is greater than the amount of phosphorus that's been being delivered acre for acre from agricultural areas. So this relatively recent land conversion from agriculture and forestry to suburban land uses is an important recent change that is contributing to the health problems that we're seeing in the lake.
As Vermont's land use continues to transition from agriculture and forestry to a more suburban landscape, an important consideration is in the higher altitudes.
One of the projects that I'm working on is looking at what the effects are of suburban development, recreational development in the mountain landscape, and how that development affects water quantity and water quality. And what we really want to know is, are there ways that we can develop where we can minimize what those effects are on water quality and water quantity? That doesn't mean we shouldn't manage the landscape, it just means that we need to understand what those effects are. We're doing intensive field-based studies. Like this winter, we'll do an intensive snow monitoring study to look at the distribution of snow in the mountain landscape.
What we were doing with the University of Vermont and the USGS is to measure the thickness of snow on the ski trails We want to do that because we want to know what the volume of water is, what will be the water runoff when it all melts. We could record the data very quickly, 48 times per second. We were taking a reading. One run down the mountain might have lasted 2 minutes, 120 seconds, there were 6,000 readings. Simultaneously, we were measuring the GPS coordinates of where he was, so we'll be able to recreate that.
Typically what we want to understand in forest hydrology is how can we manage the forest, extract timber from our forest, develop the forested landscape, but reduce the potential of that forest management to degrade our water resources.
Clearly, Vermont scientists are quantifying the numerous parameters contained in our water system. Through a research grant from the National Science Foundation and with support from Vermont EPSCoR, researchers are compiling a complex model for the Champlain Valley watershed, working to forecast Vermont's water quality well into the future.
We have amassed a considerable amount of data on the lake, on land uses within the watershed, on the climate, on urbanization patterns, agricultural patterns, and so forth. We're currently working in the EPSCoR program on a new and exciting program in complex systems. There are interactions, there are feedbacks, there are loops that we don't fully understand. And so a part of what our complex system effort is about is in developing the tools that will allow us to expose that complexity, to understand those feedbacks, to understand those so-called emergent properties.
A system comprises many interacting entities. Those entities could be molecules, they could be people, they can be animate or inanimate. If you think about something like a watershed, it's a huge complex systems model and has lots of different processes going on with different spatial scales and different temporal scales. So in a watershed, you've got the physical hydrological processes, which are governed by nice physical laws of motion. Where do the streams go? What sediment is coming down in? How much erosion do we have going on? What's going on with the floodplains or channelization? Those kind of things affect the water a lot. What's going on with the land use patterns? Is it farmland? Is there a lot of manure spreading going on that's putting various contaminants into the water? Is it a new Walmart with a big pavement that's increasing the non-permeable area, the ski areas, etc.? So all of these things affect the processes related to the water. But of course, it's not just the water-related processes that are relevant too. It's also the climatological inputs that are coming into this thing, the flora and fauna, what animals and plants live around, and how do they interact with the whole hydrological and non-hydrological system. There really are no subsystems. It's all one big system. I would say the main characteristics of a complex system are that they're nonlinear. That is, they're not just additive. You can't look at the parts. You've got to look at the interactions. They're dynamic. That is, they vary over time. There is no global control. That is, the system behavior is governed by the local behaviors of these interacting entities.
The idea of complex systems modeling is to put all these equations together, to look at the feedbacks and the interactions, and then to see if we can predict sort of the trajectory that the ecosystem is going on. If we understand the way that we're moving into the future, we might be able to alter that path into the future, and that's the goal, to come out with a better future condition based on understanding the trajectory that we now have. And again, that reflects everything that went before, from 10,000 years all the way up to what happened yesterday.
About 6 or 7 years ago, the U.S. Forest Service initiated an effort to try and do a campaign around the most valuable resource that comes out of our forests. And they tried to emphasize the fact that one, if not the most valuable resource that comes out of our forests is clean water. And so if we can manage our forests not only to get wood products out and non-timber products out, but also clean water out of our forests, then we've got it made.
We have often turned to a hard-engineered, man-made solution to complex problems. One of the things that we are particularly interested in the Rubenstein School of Natural Resources and the Environment is in looking at alternative solutions, solutions that work with nature, so-called ecologically designed solutions.
A lot of people would look at a forest and say that forest is worth, there's like 20 million board feet in there and I can get 16 cents a board foot. And so 20 million times 16, that is what we can get out of it. Or they can look at the lake and they say, well, we can fish for so much fish there, or we can actually get people to come and be tourists on that lake. You know, and so what is the direct market value that we can get out of these ecosystems? In ecological economics, we actually making this argument that there is actually more value than just market value to the systems. There are things of systems in a forest that we cannot necessarily market.
I think science is absolutely key, and I think students these days understand that science and technology are extremely important to the future of not only their own lives, but our planet. As we move forward in this world with 6 billion people and a changing atmosphere and a changing climate, all of those things I think conspire to make science even more important than it has been in the last century. I think you see a lot more scientists now who are willing to take stands on issues, who are willing to be vocal, who are willing to say, this is my science, this is what I know, and this is what it means for society. And I think that's a good thing.
Science allows me to think of a question, to state a hypothesis about the way the environment ought to work, to design an experiment, to test that hypothesis, and then to see if I was right or not. And if I was right, that helps me understand the environment better. Even if I'm wrong, that helps me understand, because I can now ask, well, why was I wrong? And I can know my environment, I can know what water is doing and have a deeper appreciation. But that doesn't mean that I don't also like to sit by the edge of the lake and watch a nice sunset and know my environment in a much more personal and spiritual way as well.
It is undeniable that to sit by a body of water gives us a special feeling of connection. Whether it's a raging river, a cattail-rich wetland, or a crashing ocean shoreline, water is essential in our lives. Not only are we primarily made of water, but we're drawn to the self-reflections that bodies of water trigger. Understanding how to secure our water quality locally has direct implications in securing global water supply, given the connection that all humanity has to fresh water on the planet. Thank you for joining me this week as we learned about the geological and human events that have formed the nature of water in the Green Mountain State. I'm Amy Seidel. Join me next time for more Emerging Science.
Emerging Science is a Vermont Public Television production in partnership with and funded by Vermont NSF EPSCoR. EPSCoR, supporting science and engineering in Vermont colleges and businesses and encouraging young Vermonters to seek careers in science.